Okay, so whenever we're talking about finding all solutions, now remember they sometimes call it roots, they sometimes call it zeros, solutions, and they're all talking about basically the x-intercepts for all of these functions. So in the previous section, we had looked at the rational zero theorem, which is where we took the factors for our constant term and divided them by the factors of our leading coefficient. So that gives you a whole list of options which we can consider for our zeros or our solutions for the polynomial function. Then we talked about multiplicity. So sometimes these roots can occur in multiplicity. So if you're a fifth degree polynomial and we have 5 maximum roots, some of them can be the same root with a multiplicity, right? So we had talked about that. We talked about the conjugate pairs theorem. So the idea with the conjugate pairs theorem is if you have imaginary solutions, they're always going to come in pairs. So you will have the a plus bi, which means you're also automatically going to have a minus bi as your root for your polynomial function. So all imaginary numbers are going to come as conjugate pairs in our solution. We talked about Descartes' rule of signs. So Descartes talks about how many positive real roots we can have, how many negative real roots we can have, and how many imaginary roots we can have for a given polynomial function. So that's what Descartes' rule talks about. And then Theorem and Bounds, which was the last thing we had talked about, is essentially putting a upper bound and a lower bound on which numbers I can use. And that actually helps us discard some of those options that we come up with our rational zero theorem. So you can narrow down your roots in that case. So let's look at how we can apply all of these different theorems and rules to find the solutions for this polynomial function here. So we've got 2x to the third minus 5x squared minus 8x plus 5. Okay, let's go ahead and see what we can do here. So we'll start with our rational zero theorem actually. So the first thing we'll do is start with factors of positive 5. And these will represent our p-values. So what can we break down 5 into? Yeah, 5 and 1, or 1 and 5. Same thing with the leading coefficient. So we're looking at factors of 2 from the 2x to the third, which we designate as q. And again, what does 2 break down into? Yeah, 2 and 1. They're all prime numbers, so you don't really have too many options to list them. So once you get your factors for each of these values, now we can go ahead and see what our rational zeros will be. So this is where we start by listing them, p divided by q. So I'm going to start with 1 and 5 and divide them by the number 1. So 1 divided by 1, 5 divided by 1, and of course we repeat that with dividing by 2. So 1 divided by 2 and 5 divided by 2. And remember, with rational zero theorems, we always need to consider positive and negative for each one of these options. Just cleaning these guys up, I will have positive and negative 1, positive and negative 5, positive and negative 1/2, positive and negative 5/2. So remember, rational zero theorem just gives us all the possible zeros that we can have. Now it's our task to try and narrow these options down. So with rational zero theorem, now let's move on to actually our Descartes' rule of signs. So this will tell us how many positives and negatives and imaginary numbers we should have. So Descartes' rule of signs. So this is where we take our polynomial and look for variation of signs. So that's going to be 2x to the third minus 5x squared minus 8x plus 5. So how many variations do you think is happening in this polynomial?
2.
2. We're going from a positive to a negative, so that's our first variation, right? We're going from negative to negative, so the sign didn't change. And then we're going from negative to positive, so that's our second variation. So when you do the original polynomial itself, that tells you at most how many positives we can have. So these two variations are actually telling us that we can have 2, or remember we decrease this in pairs of 2. So 2 minus 2 will be 0. So I can have either 2 or 0 positive real roots. Okay. Then what did we do to figure out how many negative real roots our function would have? Does anyone remember? Yeah, any?
P of negative x.
Yeah, you just replace your x with negative x and see what happens with your signs. So this will be 2 times negative x to the third minus 5 times negative x to the second minus 8 times negative x, and 5 has no x on it, so you just bring it down as plus 5. Okay, so now remember, if you have a negative base with an odd exponent, the negative sign will stay. If you have a negative base with an even exponent, it becomes positive. So negative x to the third power, negative base, odd exponent means negative sign will stay. This guy will now become negative 2 x to the third. Then in my second term, I have negative x to the second power, so that's negative to an even exponent. This negative sign will actually become positive, which means the negative 5 does not change. You will still be left with negative 5, and this guy will become positive x squared now. Okay? On our third term, we have negative 8 times negative x, so negative times negative will become positive, so that's positive 8x, and of course, our positive 5. Okay, so once you clean it up, you're again looking for how many variations are there in our signs. So what are we noticing in this guy? We're going from negative to negative, no change, negative to positive, 1 change, positive to positive, no change, right? 1 variation or 0 variations are always really good for us, because if you get just that option of 1 variation, then you know we will definitely have a negative root in our polynomial here. So 1 variation means there's exactly 1 negative real root. So now you can see how we got 2 or 0 positive real roots. So we don't know, are we going to have 2 positives? Are we going to have 0 positives? But when you get 1 negative, then you know no matter what positives and imaginary solutions look like, we definitely have 1 negative in all options that we go forward with. So that's kind of what we're saying. If you get just a 1 variation or no variations, that's what we're always looking for. But you know, we saw examples last time, and we know that doesn't always happen. Okay, so what kind of possibilities are we looking at here? We can have 2 positive real roots, 1 negative real root, which means how many imaginary will our polynomial have? 0, because this is a third degree polynomial, right? The original is 2x to the third, so that's a third degree polynomial. 2 plus 1 adds up to 3, which means we have no room left for any imaginary solutions. What's our other possibility?
0 positive real roots.
Yeah, because remember your positives is 2 or 0, so you can have 0 positive real roots. How many negative? 1. Yeah, 1 is a constant, so we will definitely have 1 negative real root, which means how many imaginary?
2.
2, because it should always add up to a total of 3 roots. So we will either have 2 positive and 1 negative, or 1 negative and 2 imaginary. That's what Descartes' rule is telling us. Now let's look at Theorem Unbelt. So this is where we find our upper and lower limits. So for the upper limit, remember you start dividing by 1, 2, 3, 4, 5, all positive numbers, till we get non-negatives on our bottom row of our synthetic division. Non-negative means they can be 0 or positive numbers. They just cannot be a negative on that bottom row. So let's start dividing by 1. Now what numbers do I put inside my synthetic division? And you guys have the whole back page blank, so if you run out of space, just use the back page.
2, negative 5, negative 8, 5.
Very good. 2, negative 5, negative 8, and 5. So synthetic division means bring the first number down as it is. And then what do we do?
Multiply.
Multiply. So we're multiplying 2 times 1, which gives us 2. And then what happens with negative 5 and 2?
Negative 3.
Yeah, you're adding them. So negative 5 plus 2 will give us negative 3. We go back and multiply. Negative 3 with 1. And when we add negative 8 and negative 3? Negative 11. But obviously, the moment you hit the negative number, you don't need to go forward. I will, however, go forward, and I'll tell you why in a minute. When I multiply negative 11 with 1, I get negative 11, and these guys add up to negative 6. So you remember how positive 1 and negative 1 are our possibilities in the rational 0 theorem? So obviously, 1 doesn't work out because we didn't get a 0 remainder. So that's why I wanted to finish the 1. Since they are both part of our rational 0, let's go back. So you can see how positive 1 and negative 1 are part of our root. So we just wanted to check and see, do you get a 0 root for those numbers or not? Okay. So we're kind of using Theorem of Bounds to help us check. So in more than one ways, this guy doesn't work out for us. Okay, so 1 did not work out, which means we move on to positive 2. Will we get non-negatives with this one? What's that? 2 times 2 is 4. Negative 5 plus 4? Negative 1. Which again, the moment you hit a negative, you can stop working with that. So, will 3 work out for us? No? Three 2s are 6, which gives us a positive 1, but this is where it's going to fail because 3 times 1 is 3, and you're going to get -5. So 3 does not work out either. He's gone. Okay, what does this guy do? 4 2s are 8. That's a +3. That's a 12. What is that? A +4. 4 4s are 16. The 4 works? Yeah. So that's going to be our upper limit. Okay. All right, let's check and see for our lower limit, or actually lower bound. Shouldn't be a limit. Should be a bound. Okay, now remember -1 is also one of our rational zeros. So we're going to check this one all the way to see if we get a zero remainder or not. So this guy is again 2, -5, -8, and 5. Now, when you're looking for lower bound, what should your bottom row of synthetic division have? Yeah, they should alternate in sign, right? So positive, negative, or negative, positives. Bring that first number down as it is. So this guy will give us -2, -7. So far, so good. Negative and negative is positive. But this gives us -1. So as far as lower bound goes, this does not work. But again, I just want to see if we have a zero remainder or not for our rational zero. So negative times negative is positive. And of course, that guy adds up to a 6, not a zero remainder. So it's not a lower bound. It's not a zero. Okay, what about -2? Does that work? I don't think -2 works, does it? Okay, which one will? Well, so far we're looking good, right? Bring down the 2, -4, that adds up to -9. Positive 18, that's 10, so that's -20. It is -15, isn't it? Yeah. I thought you said no.
No, I didn't say anything.
You shook your head at me. Don't trust him. Okay, so that is actually our lower bound, right? Because we're alternating in signs. We've got positive, negative, positive, negative. So as far as our bounds go, our x is going to be between +4, which is the upper bound, and -2, which is our lower bound. So what that's telling us, -2 and +4, -2 and +4. Of course, we checked these guys for zeros and they were not. So both of these options are out. What else can I discard for my bounds from -2 to +4? Yeah, I can take out both positive and -5s, right? Because they are not within that range. I can take out the -5/2 because -5/2 is -2.5, which will be outside. So I'm actually going to take out the negative option from there. 1/2, positive and negative is well within that range, right? And +5/2, of course, is within that upper bound. Okay, so let's start checking with what we have left behind. What do we want to start with? We've got 3 numbers to choose from.
+1/2.
All right, +1/2 sounds good. And this page just gets getting longer. Okay. So this is where we're now checking with positive 1/2. Still obviously using the same values from our polynomial. So that's 2, -5, -8, and 5. And let me see what you guys come up with. Remember, this time we're checking to see if these guys are zeros, which means you're actually looking for a zero remainder. So we don't care if it's alternating in signs, if it's non-negatives and none of that, because we're not looking for bounds. We're looking for a zero remainder.
Positive 1/2 works.
It works?
I think so.
Okay, let's see. We're multiplying we're multiplying 2 with 1/2, so that ends up giving us 1. What's that, a -4? So we're multiplying -4 with 1/2.
-2.
So that'll come out to be -2, which is -10, -5. Yeah. Which is giving you 0 remainder, alrighty. So if it is a 0 remainder, positive 1/2 is one of our roots. Now I wouldn't go back and check for the other two numbers, which was -1/2 and 5/2. Once you hit your 0 remainder, what did I tell you? What should we do next?
Plug it back into the original equation. Or no?
If you put it back into the original, you'll just get 0 as the answer. And since it's a 0,
You use that somehow to find your other two. I can't remember.
Anybody remembers? Amy?
Don't you like factor put those back into the equation, so it'd be like 2x squared minus 4x minus 10.
Yeah, you work with the quotient, right? So now we have to look at the quotient and factor it out. So this is our quotient. And it's always 1 degree less than our polynomial, right? So since this was a 3rd degree polynomial, this is a 2nd degree quotient. So that's correct. It's going to be 2x squared. Oh, what did I do? I have no idea. It's so weird. Okay, 2x squared minus 4x minus 10, set it equal to 0 and see how you can factor this out. So where would you start?
Put the half into your x's, or replace your x's with 1/2.
No. So we're done with that guy. We know he's one of our roots.
Oh.
So you're just solving 2x squared minus 4x minus 10 like it was a quadratic equation.
Do you factor out 2?
You can, yeah. So start by factoring out a 2, which will give us x squared minus 2x. And since this is an equation, we are setting this equal to 0. You can go ahead and divide both sides by 2. And basically simplify your quadratic equation here. X squared minus 2x minus 5. Can I factor x squared minus 2x minus 5? Factors of -5, that will add up to give us -2. No, because 5 is what? Just 5 and 1, right? And either way you add or subtract, you're not getting -2. So what can we do if factoring doesn't work? Quadratic formula, yeah. When in doubt, use quadratic formula. So what's our A coefficient here? 1, yeah. All right, let me see what you guys come up with for your x values here. you can see that we got 1/2 as our remainder 0, which means 1/2 is one of our roots. 1/2 is a positive number. So if this is a positive number, that means our possibilities are going to be 2 positives and 1 negative. That means obviously you should not get any imaginary answers when you solve your quadratic formula. And none of these other options are also going to work out. So -1/2 doesn't work, +5/2 doesn't work. So the only thing we got out of this whole list of 8 options was just that +1/2. And then from Descartes's, we're getting 2 positives, 1 negative. And from our Theorem on Bounds, whatever answers you get should stay within -1, -2, and 4. Okay. So make sure when you're simplifying this, all of those are still staying true. So when you simplify your quadratic, what will it simplify into?
±square root of 6.
So what happens with the 2 divided by 2?
Oh, is it 1 plus?
It becomes 1, yeah. And then plus or minus, so these guys become a 1. These guys cancel out, leaving us behind with the square root of 6. So the roots or solutions of our polynomial are going to be this 1/2 from here that we used first, which gave us the 0 remainder. So that 1/2 is one of our roots. And then the other 2 roots are coming from our quadratic formula here. So 1 minus square root of 6 and 1 plus square root of 6. Can anybody tell me what the decimal approximations for these terms are, so we can see if we stay within -2 and 4?
2 or 1 plus square root of 6, I think is 2.45. No.
3.4.
Yeah, so this guy comes out to be approximately 3.45, and what is this guy approximately?
1.45.
-1.45.
-1.45.
And again, the decimal approximations are not our answers. It's the exact numbers which are. That was just for us to make sure that the Theorem and Bounds work. You can see I have 2 positive solutions, 1 negative solution. So that's our Descartes's rule. And then of course from the rational zero theorem is where we got that 1/2. So, and this was just a 3rd degree polynomial. If this was a 4th degree, 5th degree, then of course you're going to get more options, more things you have to narrow down. But the process will always stay the same. So start with your rational zero theorems, get your list of possible solutions from there. Then use your Descartes's rule of signs to see how many positives, how many negatives, how many imaginary we're going to have. And then Theorem on Bounds to see what our lower bound and upper bound is going to be. Once you cancel out, narrow down that rational zero possible answers, then of course we just use synthetic division to see which ones of those options is actually going to work. And once you get that 0 remainder, stop right there. Take your quotient and then start breaking it down, start factoring it down further to see what other options you can get. So just in that same sense, if we had any imaginary solutions here, remember what we talked about, how they come in conjugate pairs. So they would have also come with a plus or minus of their imaginary answers, which in this case, we just happen to get them in real numbers instead of imaginary. Any questions on number 6 here? All right, guys, that's the end for 3.3 then.